Okay, it's 8:30, so let's go ahead and get started today. All right, good morning, everybody. How's everyone doing on this fine Wednesday morning we have here?
Doing all right so far.
Doing pretty
Good,
good.
good. That's good. We end of week 2 this semester. Um, the semester always goes fast, but at the same time goes slow. It's always kind of a weird thing. Even when you reach kind of this side of the schooling, it's always the same feeling. It feels too fast because there's always so much to do in too little time, but it also slow because it's not Christmas yet. But that's just how the semester goes. Okay, so the plan today is we're going to continue our discussion on hydrostatics. So I think where we left off last time was, we came up with the expression of how pressure varies in a fluid. So today we're going to be doing some examples and seeing how that, is actually applied in some situations. Okay. But before we get started with that, are there any questions I can answer before we get started?
Will our homework be graded based on like completion, or would it actually be graded on like correctness?
Yeah, that's a great question. Actually, that's one thing I've been meaning to address, but it always just slips my mind. So it's good. It's good that you asked that question. So normally, what I do is I do kind of like a mix of both. So first of all, I check to make sure that you did everything and you gave it a good effort, and that's worth half the points usually. And then I go through again and I correct every problem just for correctness. But because I have a lot more students this semester than what I'm used to, just because of the virtual instruction. What I'm going to do instead is, first of all, I'm going to check for completeness, so that's still the same. But for correctness, I'm just going to look at just one of the problems on the homework. So I won't tell you what that problem is beforehand because I want you to try on all the problems. But I'll just be grading one of the problems for correctness. And the way I'll be grading that is basically the same as how I grade exams. So it's I try to be as generous as I can with partial credit. So even if you can't get the full problem, definitely give it your best effort on every single problem, because I like to award the process, because doing engineering in a classroom is in a sense is different than doing it in the real world, where in the classroom we're trying to learn the process and learn the concepts of doing these kinds of problems. So I award the process as much as I do the more so than the final answer itself is worth just very little points for me. But if you can show me the process of you use this equation and it's neat and it's organized and I can follow what you're doing, that's going to be worth most of the points. So for this semester, I'm just going to be grading just one of the problems for correctness, but I'll grade it just like I do an exam. So I give as much partial credit as I can. Yeah. All right. So there's a question. So do we upload the assignment as one PDF on Canvas by today? Yes. So if you can upload the assignment as one PDF, that'd be great. I was a little bit late in posting the homework last week, so the homework's actually due tomorrow by 11:59 p.m. So if you upload the PDF by tomorrow at 11:59, then that's still going to be considered on time. Yeah. All right. So there's a specific question on the homework, 3C. So let me pull up the homework document. All right, 3C. So 3C is asking you, what is the characteristic pressure for wind patterns over the Pacific Ocean? So for that one, one thing you can look up is, what's like the typical air pressure over the Pacific Ocean. So you can just look up maybe like an average pressure, or you can look up just like atmospheric pressure around the Pacific Ocean, and that would be good for that one. Mm-hmm. All right, any more questions before we get rolling today?
Will there be a homework number 2 for next week?
It's not going to be due next week because we've just kind of scratched the surface for hydrostatics, so it'll probably be due in 2 weeks. Yeah, so I'll probably have that posted early next week, and then you guys will have until I guess that would be week 4 to complete it. Yeah. Okay. So if you guys think of any other questions, definitely stop me anytime during the lecture or send it to the chat. But if not, I'm going to go ahead and get started. Okay, so last time, where we ended was with an expression for, how pressure varies in a static fluid, right? And so what we said was that, pressure only changes in a fluid with respect to depth. And so in order for you to experience a different pressure in a static fluid, you actually have to go deep, right? So the expression that we came up with was dP, P with the ponytail, so that's pressure, okay, dy is equal to minus gamma, right? So remember, gamma right here is specific weight. Okay. And specific weight, the way that you get that is you multiply your density by your gravity. Okay. So every fluid has a density. Usually the density is easier to look up than the specific weight. And so if you have the density, you just multiply by gravity, and then you get specific weight. Okay. And so since specific weight's a kind of a new concept, let's let's go over the units. Okay. And so the typical units for specific weight would be some kind of force. So the SI unit for force is newtons, and that's divided by meters cubed. Okay. Right. And so this tells you that the derivative of pressure with respect to depth is equal to the specific weight. But for actual problems, a lot of times it's easier to work with kind of 2 points, right? So if you have kind of a tub of water, and you have 2 points here, so we'll call this point 1 at the bottom, and we'll call this point 2 up here. Okay. And so if we integrate the expression up there, we get something that's actually more useful for calculation. And so the difference between P2 and P1, this is going to be equal to minus your specific weight times the difference in height. Okay. Okay. So this formula here is a bit more useful. Another form of this equation, where if you know the actual height difference in between the two, so the difference between 0.2 and 0.1 is has some height difference h. Another form of this equation could be P2 minus P1 is equal to minus gamma times h. Okay. So these are all the same. So basically, if you want to find the difference in pressure between 2 points in a static fluid, you take their height difference and then you multiply it by the specific weight minus the specific weight. Okay. Right. And so the key to these hydrostatic problems is that the only thing that matters is the height, right? And so I think we ended the last time saying if you travel kind of in a horizontal plane, you're always going to experience the same pressure because you're always going to be at the same height. Okay? And in particular, when you're looking at containers of fluid, it doesn't matter what the container actually looks like. As long as the height difference is going to be the same, then the pressure difference is the same. So I'm going to draw some examples here. So say you have kind of a narrow fluid, a narrow container, like you have a beaker. You can have a really wide one like this, right? Or you can have kind of a really funky container like this, right? So in all these cases, the pressure difference between these 2 points is going to be the same, because remember what's important for these pressure differences is the height. So the shape of the container doesn't matter. So it's a little bit I think non-intuitive at first, because you would think that if you have a really skinny container, this would have a different pressure difference than something that's really wide. But they actually have the exact same pressure difference because their height difference is the same. Okay. And so one other thing before we move to the next slide is that you'll often see me use this triangle. So I'll put this little triangle on top of the surface of the fluid, right? And so this is a symbol that I use to denote a free surface. Okay. And so free surfaces, what that means is that that surface is connected to the atmosphere, okay? So if you look at like a typical glass of water that I have right here, you see that the surface of the water is, you know, right here, okay? So this would be a free surface right here because this is connected to, you know, atmospheric air that's kind of around us, right? And so this is a really important point for calculations because usually what we assume for these hydrostatic calculations is that any surface connected to, any surface that's free right here connected to the atmosphere, this one has zero pressure, okay? Okay. And so this is a really useful reference point for when you're doing calculations, because you can see from our formulas here, the only thing that we can do is pressure differences, right? But if we want to solve for a specific pressure, you know, we need to have some kind of reference pressure from which we can, you know, draw our reference. And a lot of time that reference pressure is going to be the free surface where the pressure is going to be equal to 0. Okay. All right. Are there any questions on this before I move forward? Okay. Okay, so let's do an example just to kind of illustrate these concepts. Okay. And so let's say that you know, we have a gasoline storage tank, so it looks something like this. So we have kind of a narrow part up top, and then it gets a little bit wider down here. Okay. And down here is the bottom of the tank. So this is like the ground. Okay. And then we have two different fluids in here. Okay. So up top right here we have gasoline. Okay. And then below the gasoline we have water. Okay. And then let's say that we have our free surface up here. Okay. So this is free surface. So P equals 0 here. Okay. And it's the free surface because I drew that little triangle symbol there. Okay. Okay, so let's give this some numbers. So let's say that we know the specific weight of the gasoline. So the specific weight of the gasoline is given by 7,200 Newton per meters cubed. Okay. And then this specific weight of the water will be 9,800 Newton per meter cubed. Okay. Okay. And so in this problem, what we're interested in is we're interested in solving for the pressure. Okay. And so we, first of all, we want to solve for the pressure at the interface between gasoline and water. Okay. And then two, we want to solve for the pressure at the bottom of the tank. Okay. And so the way that we're going to do that is we're going to use the formulas that we had on the previous page. Okay. Oh, and we also need to know the height differences. Okay. So this height right here will be 0.5 meters. And so so that's the height difference between the top or the free surface and the gas water interface. Okay. And then the distance between the gas water interface and the bottom is 0.1 meters. Okay. All right. Any questions on the setup for this example? Okay. So let's work on part one first. Okay. So we want to find the pressure at the interface between gas and water. So we want to find the pressure at this interface right here. Okay. Okay. And so let's use our formula. Okay. So this is pressure at gas water interface. Okay. And so let's use our formula. So our formula for pressure difference in a fluid is P2 minus P1 is equal to minus gamma times H, okay? And so in this problem, we need to determine, what is going to be 0.2 and what is going to be 0.1, okay? Okay. So in this case, we need two locations. It would help if we picked a location where we know the pressure already. So let's pick the free surface here, okay? So this will be our 0.2, okay? And then our 0.1 will be at the interface between the gas and the water, okay? So these 2 points are convenient for multiple reasons. So first of all, picking point number 2 at the free surface, we know exactly what the pressure is there. So we know P2 is going to be equal to 0. So that's going to be useful for our formula. Okay. And then the other reason that it's convenient is that we know the height difference in between them, right? So we know that the height difference is going to be 0.5 meters. Okay. All right, so there's a question in the chat. So the question is, are the liquids in one container and the density is divided them? That's correct. So all these fluids are in the same containers. There's no solid interface between them. But because of the chemistry between these two fluids, we call them they don't mix. It's like you put oil and water into a container, then they separate out kind of really naturally. And since water is more dense than gasoline, that one goes down to the bottom. Right? All right. So there's another question in the chat. So it doesn't matter where 0.1 and 0.2 is. It does. So you want to pick, the 2 points such that, usually you pick the 2 points such that the pressure at one of the locations, and you want to pick the 2 points. You want to pick 2 points where the height difference in between them. So in this case, we know the height difference between 0.2 and 0.1. So that's a good location to pick for this example. And 0.2 is really convenient because we know the pressure there because that's the free surface. Yeah. Okay. So let's go ahead and plug those guys in. And so P2 is going to be equal to 0. So since that's the interface, H right here is going to be equal to 0.5 meters. Okay. Okay. And then for the specific weight, since we're just traveling through the gasoline, so we just went from the top of the gasoline down to basically the bottom of the gasoline, the only specific weight that we need to use is that of gasoline. Okay. And so the specific weight of gasoline is 7,200 newtons per meter cubed. Okay. And so we plug all these guys in. Okay. These two negatives cancel out. Then we get P1 is equal to 7,200 multiplied by 0.5. Okay. And this gives us 3,600 pascals. And so the reason we got pascals is the meters from the height will cancel out with one of the meters in the denominator for the specific weight, and so we get newtons per meter squared. And another way to express newtons per meter squared is with pascals. Okay. All right. Any questions on that on the first part of the example? Okay. So now let's do the next part of the problem. So the next part of the problem asks us to find the pressure at the bottom of the tank. Okay. So the bottom of the tank being right here. Okay. And so we're going to use the same formula that we did before. So we're going to do P2 minus P1 is equal to the specific weight multiplied by the height. Okay. But since we're going to a different location, we need to pick our points again. Okay, so we actually have a few options here. So we can keep 0.2 at the top of the container. So you can do the problem like that. But another way that's more convenient is we can pick location 2 to be at the interface between gas and water. Okay. And so the reason we do that is because we did part 1 of the problem, we know what the pressure at this interface is now. Okay. And so since we know what the pressure is here, we can actually use that as a location. Okay. And then since we want to know the pressure at point 1 at the bottom of the tank, we'll make point 1 to be at the bottom. Okay. Right. And so these 2 points are also convenient because we also know the height difference between them. So we know that there's a height difference of 0.1 meters in between these two. Okay. And so with these 2 locations, we have basically all the information we need to solve the problem. Okay. So let's go ahead and plug that in, right? So we're going to use the same formula. So we have P2 minus P1 is equal to minus gamma H. Okay. And so with these 2 new locations, we're going to plug in for P2. So P2 in this case is going to be our solution to part 1. So this can be 3,600 pascals. Okay. Right. Okay. And so the next thing that we can plug in is the specific weight. And so since, going from this new point 2 to this new point 1, we're traveling through water, right? And so the specific weight that we're going to use there is that of water, right? So the specific weight of water, which is given to us in the problem, is 9,800 newtons per meter cubed. Okay. And then finally, the height difference between them is going to be 0.1 meters. Okay. And so we have everything that we need in this formula. So the only thing that we don't have is P1, where P1 is the pressure at the bottom of the tank. So let's solve this expression for P1. So we have, we move P1 to the other side, and we move the gamma H over to this side. So you have P1 is equal to P2 plus gamma WH. Okay. And so we plug all the numbers in, and then what we get is P1 is equal to 4,580 pascals. Okay. All right. Are there any questions on this example here? Okay. So let's do another example. Okay. So this one's more, there's no numbers on this one, but hopefully this is interesting. So I know some of you guys in your introduction emails mentioned that you're interested in hydraulics. So this is kind of a very rudimentary, model for hydraulics. So real hydraulics are a lot more more complex than this. But this gives you kind of the general idea between. Okay, so this example, we're going to do a hydraulic jack. Okay. And so the geometry looks a little something like this. Okay. Right, so you have a tank of fluid that looks something like this, right? So there's fluid in here, okay? Fluid's going to fill this cavity. And so this is this is where you basically put your input. Okay. So normally with the jack, what you're aiming to do is you put some input force, and then there's going to be some output force. And because of the design of the jack, there's going to be an amplification of the force that you put in. So this is where you put your input force. Okay. And we'll say that this piece right here has an area of A1. Okay. And then over here on the right, we have a much bigger plate. So we have A2 for that plate. And then that's where your output force is going to be. So So the way this works is that on the input plate, you're going to put in some force. So that's where you're going to be pumping down basically. And then at the output plate, you're going to have, an output force. And the idea is that, because of the design of the jack, the output force is going to be much higher than the input force. Okay. And so what we're interested in finding is we want to develop an expression for the mechanical advantage. Okay. And so the mechanical advantage is basically the ratio of the output force over the input force. Okay. And we're going to use hydrostatics to basically, develop this expression. Okay. All right. Are there any questions on just the, or just the idea behind the jack, or just anything in the diagram? Okay. Okay. So let's start analyzing this. Okay. And so since we know that there's a fluid that's in between these two guys, so it could be air, it could be some kind of hydraulic fluid like water or something like that. What we notice here is that the input and the output plates, they're at the same height. And what do we know about fluid? Two different points in a fluid that are at the same height, we know that they're going to be at the same pressure. Okay. And so this is true because there's a fluid that's connecting them. So you basically have just it's a kind of a complicated container, but we have just one container of fluid, and we have two locations here at the same height, so they have to be at the same pressure. Okay? And so what we're going to do is we're going to use the fact that they have to be at the same pressure to get a ratio of the output force to the input force. Okay. Okay. So let's go back to our understanding of pressure. So remember, pressure is nothing more than just a force divided by an area. Okay. And so what we can do is we can take, the input force that we're putting in on the hydraulic jack, and then divide it by the area of the plate, and that's going to be that's going to be our expression for the pressure. Okay. Okay. And so the pressure at the input plate is basically going to be the force that we're pushing down with, divided by the area, A1. Okay. Okay, so we can make the same expression for the output plate. So at the output plate, we have the output force that's going out divided by the area of that plate. Okay, so we have output force divided by A2. Okay, and so because we're in a static fluid that's not moving, these two quantities have to be the same. So we can set them equal to each other. So we have input force divided by A1 is equal to output force divided by A2. Okay. And so now that we have this expression here, we can manipulate it to get our expression for mechanical advantage. Okay. And so what we can do is we can take the input force and divide both sides by it, so it ends up in the denominator here. And then after that, we can multiply both sides by A2, and then put A2, which puts A2 in the numerator over here. And then what we get is A2 over A1 is equal to output force divided by input force. Okay. And so our expression for mechanical advantage, which is output force over input force, is equal to the ratio between the two areas. So the bigger the ratio between those two areas, you either have a much bigger A2 or a much smaller A1, you're going to generate much more mechanical advantage from this hydraulic jack. Okay. Right. So this is kind of a very simple, simplistic, model for hydraulics, but it utilizes the fact, that locations at the same height within a static fluid have to have the same pressure, and then we use that fact to generate this expression for mechanical advantage. All right, any questions on this example? Yeah, so the question is, what is mechanical advantage? So mechanical advantage is this guy right here. So it's basically the ratio of how much output force that you generate per input force that you put in. Okay, and so the higher this ratio is, so the higher, we can say the mechanical advantage is like 4x, right? And so what that means is that for every Newton that you put in, you get 4 newtons of output. So it's how much advantage this jack is giving you. Yep. All right, any more questions on this? Okay, so let's move on to the next concept, which is standard atmosphere. Okay. So standard atmosphere, we're basically going to be talking about atmospheric pressure. Okay. And so just right after I told you that the free surface is 0. Oh, is Zoom crashing for everybody? Is everyone still here?
Crash for me.
It just crashed for me.
Oh, okay. Is everyone back? Okay. Okay. Looks like everyone's back. So let's keep going. So standard atmosphere, what we're going to be covering here is, what is the atmospheric pressure, or what is the pressure of kind of the ambient air around us, right? Okay. So for calculations, a lot of the time, what we assume is that the atmospheric pressure is going to be 0, just because that's really convenient for calculations. But it's not actually 0. So there's actually the air around us, air is a fluid. It's actually exerting some kind of pressure on us. Okay. Okay. So we don't live in a vacuum. So usually, usually when you say you have 0 pressure, that means you're in a total vacuum. But that's not the case. So all the air that's in Earth's atmosphere is exerting a pressure on us. Okay? It's just a lot of times we just ignore this in problem solving because the atmospheric air is all around us. There's always going to be that constant offset. So we kind of just ignore it. So there's 2 kinds of pressures that we have associated with this. So the first pressure is the absolute pressure. Okay. And so the absolute pressure includes the effects of atmosphere. Okay. And so another way to say this is pressure that's measured relative to a vacuum. Okay. And so kind of the upside for problem solving is that this includes the ambient atmospheric pressure. Okay. And so, another consequence of this is because it's measured relative to a perfect vacuum, it's impossible for absolute pressure to be negative. You can think of absolute pressure as kind of like, kelvins, right? From your thermodynamics class. So Kelvin is an absolute measure of temperature, where 0 Kelvin is the absolute coldest you can be in the, in this known universe as far as, science knows right now, right? So it's impossible to have negative Kelvin because 0 Kelvin is literally the coldest you can be. So absolute pressure is kind of the same thing. So it's an absolute measure of the pressure, and therefore it's impossible to be negative. Okay? But a lot of times, we don't use absolute pressures for problem solving because, because the atmospheric pressure is kind of around us all the time, we mostly just ignore it. So the pressure that we use for for problems is known as gauge pressure. Okay. And so gauge pressure is pressure that's measured relative to atmospheric pressure. Okay. Okay. All right, so you're probably wondering, what is the numerical value of atmospheric pressure? So now's as good a time as any to state it. So in reality, the pressure, it varies a lot, and kind of a lot of the variance depends on your height. So a lot of times, the atmospheric pressure that you experience is usually, depends on how high above sea level that you are. But for a good, approximation for most of us, that's kind of relatively close to sea level. A good value for the atmospheric pressure is 101.33 kPa, so 101.33 kilopascal. Okay. Okay. Another unit that you'll see often in the literature, or if you read other textbooks, is this unit of atmosphere, or ATM. Okay, and so atmosphere is a very special unit of pressure that's used to that's kind of specialized for atmosphere. Okay, and so a pressure of 101.33 kilopascals is the same as 1 ATM. So that's your kind of conversion factor right there. So if you get a problem where it gives you the pressure in terms of ATM, and you need to convert it to pascals, you can say that 1 ATM is equal to 101.33 kilopascals. Okay, and so in order to compute the gauge pressure, what you do is you take your absolute pressure and you subtract 101.33 kilopascals. Okay. Okay. And so gauge pressure, this is the one that we often use in calculations, and it's the one that we've been using for the past couple examples. Because remember what we said was, the pressure at the free surface, or anywhere that we have that little triangle, is equal to 0 pressure. Okay. And so that zero pressure it's you know, it's not absolute pressure because, you know, the top of this of the water in this glass is not at zero pressure, it's at atmospheric pressure. But just for calculations purposes, you know, we assume that, you know, that or we assume that we're using the gauge pressure just so that we can use zero pressure for anything that's at atmospheric. Okay. All right, are there any questions on atmospheric pressure, absolute pressure, or gauge pressure? Okay. Okay, so the next concept that we're going to be going over is manometry. Okay. So manometry, you know, just a little bit of a historical context. These are the devices that used to be used like in kind of the days of like Isaac Newton to measure pressure. So you know, nowadays, you know, you hardly see any of these except in you know, Hollywood movies that want to look cool and scientific. But you know, just from a perspective of learning about hydrostatic pressure and how to measure it, manometry is always going to have, you know, a place there because it's really intuitive and it uses all of the equations that we've done before. But nowadays, if you want to measure pressure, there's tons of other, you know, digital devices that do basically the same thing. But manometry was kind of the first thing that came about. Okay, so manometers are basically devices for measuring pressures, but we just don't really use them anymore because we have, you know, more convenient things. Okay, but the way they work is, you know, they use the concepts of hydrostatics. Okay, so manometer, a very basic manometer. This one's called the piezo tube or piezometer tube. Right, so it might look something like this. Okay. Okay. Right. And so you have a tube basically that's filled with fluid. Okay. We'll call this location A. And let's say that we know the height between the free surface, which is given by that little triangle, and that point A. Okay. And so, you know, what the manometer will let you do, because, you know, we have a fluid in here, and since we know the specific weight of this fluid, what this will allow us to do is it'll allow us to measure the pressure that's at location A. And so what we can do basically is we can use, you know, the formula that we had before for pressure in a static fluid. Okay, so we can do P2 minus P1 is equal to minus gamma times H. Okay. And so if we make, just like we did before, if we make location 2 at the free surface up there, we can say that P2 is going to be equal to 0 because that's going to be the gauge pressure, right? So because we assume the any pressure that's atmospheric is equal to 0, we say P2 is equal to 0, and we can make location 1 equal to point A. Okay, and so what we can say from this is that P at A is simply equal to gamma times H. And so that's the idea with manometers, where, you know, they use these kind of thin or slender columns of fluid, but, you know, because of hydrostatics, we can use those columns of fluid to measure the pressure that's inside the fluid. Okay. All right. Any questions on just what a manometer is? Looks like Zoom is crashing for a lot of people. Yeah, so thankfully mine hasn't crashed, so, you know, we'll have one, or knock on wood, we'll have one, you know, recorded video for this entire session. So, you know, you can always go back and check that on YouTube, you know, once I've uploaded it. Okay. Okay, any questions on manometers or just manometry in general? So the YouTube links are posted on the Canvas site. So if you go to the if you go to kind of the weekly outline view and you click on week 1, you'll see the recorded lectures for week 1. And then if you go to week 2, then the lectures are there. So they're on the Canvas site, but they're on the they're on the weekly viewers. Okay. So the manometer that I showed you on the previous page was kind of a very basic one. So that's called a piezometer tube. But that's while that's kind of really useful or really simple, it's actually not used that much in it's not that used that much in practical situations because you're relying on just one single column of fluid. And so if your pressure is something that's really high, your tube needs to be really, really tall in order for you to measure the pressure. And so what's used more commonly or more practically, which is a lot more space efficient, is what's something called a U-tube manometer. Okay? Right? No relation to the video sharing site YouTube. So this is kind of like the OG YouTube. Okay. And it's called that because it's a tube that's literally shaped like a U. So let me draw a picture for you guys. Okay. So it might look something like this, right? And so let's say that, same as before, we're interested in this pressure here. Okay, so we'll call that point A. Right? And so what's unique about the U-tube manometer is that we have 2 different fluids here. Okay? Right? And so just like before, on the right-hand side of the tube, we're going to have a free surface. So, that's going to be our reference pressure. Right? And so, the first fluid that we have is the fluid that we actually want to measure the pressure. So you can think of this as like the measuring pressure here. Okay. And then we have another fluid that's in the actual U part of the manometer, and this fluid is specifically designed to measure the pressure. So another name for this fluid is called the gauge fluid. Okay. Okay. And so the gauge fluid is usually very specialized for this purpose. And the characteristic for gauge fluid is that they usually have a specific weight that's really, really high. Okay. And so just a little bit of trivia. So, one of the most common gauge fluids, which was actually used in the medical industry quite a lot, was liquid mercury. Okay. And so the advantage of liquid mercury is that, at room temperature, mercury is actually a liquid, which is nice. But also liquid mercury is insanely dense. So I think it has a density that's like over 13 times more than water. Okay. And so in the early days of kind of medical technology, the way that they measured your blood pressure was they basically hooked up, they basically used a U-tube manometer like this to measure the pressure in like your arm. And then depending on the height of the column of liquid mercury, then that's what they use to determine your blood pressure. Okay. So let's actually, compute the pressures here. So remember, we're interested in the pressure at point A. So let's put in some heights here. Okay, so let's say that we know this height, this is H1, okay? And then if we go to basically the same height here, then we know H2 right here, okay? And let's label these points. So let's call the first point, point 1, and we'll call this one point 2, We'll call this 0.3, and we'll call this 0.4 right here. Okay. And so what we're going to do is we're going to use the specific weights of the different fluids. We're going to use their height differences, and then from that we're going to measure the pressure at this location right here. Okay. And so the way that we're going to do this is we're basically going to go around the U tube. So we're going to start at point A, go over to point 1, go to point 2, go to point 3, go to point 4. Okay. And then from all that, you know, we'll be able to measure the pressure at point A, okay, which we'll do on the next page. But before I do that, are there any questions on just U-tube manometry or gauge fluids? Okay. Okay. So let's go around the U-tube manometer and measure the pressure at point A. Okay. So the way that we're going to do this is we're just going to go from point to point. Okay. So we're going to go from point A to point 1, and then we're going to compare the pressures there. We'll go from point 1 to point 2, measure the pressure there. Point 2 and point 3, get the pressure there, and then point 3 to point 4. And point 4 is special, remember, because that's where the free surface is, so we know the pressure here. Okay. And so by kind of going around the horn like this and comparing all the different pressures, we'll be able to get the pressure at point A. Okay, so first let's compare the pressures from point A and point 1. Okay, so we know that point A is right here. Okay, and point 1, you can see, is right here. And so these guys are at the same height, right? And so what do we know about 2 points in a static fluid at the same height? We know that they have to have the same pressure, right? So going from point A to point 1, we can say that PA is equal to P1. Okay. So that's the first relationship that we have. And the reason for this is that they're at the same height. Okay. Okay. And so next, let's go between point 1 and point 2, right? And so these 2 points are separated by a distance h1. Okay. And so since these guys have different heights, you know that they're going to be at different pressures. Okay. And so let's use our formula from before. You know, the numbering scheme is a little bit swapped here. Normally we have 2 on top, but this time we have 1 on top. So let's take that into account. So we have P1 minus P2 is equal to minus gamma times H1. Okay. And then since we're traveling through fluid 1, right? And let me use some different colors here. So I'm using this blue scribbles to basically indicate that this fluid right here is different from this fluid over here. So I'll give this a purple scribble. And so since, you know, as we go from point 1 to point 2, we're only traveling in fluid 1. So the specific gravity that we're going, or the specific weight that we're going to use is gamma 1. Okay. Okay. Right, so let's rearrange this a little bit. And so we multiply both sides by -1. We get P2 minus P1 is equal to gamma 1 H1. Okay. But since we know that P1 is equal to PA from our first part, we can just replace P1 with PA right here. Okay. And now we have this expression as we go from point 2 to point 1. Right. So that's going from point 1 to point 2. So remember, so since we dropped a height of h1, then we have to account for that pressure difference, okay? And that's what we did in this part. So next, let's go from point 2 to point 3. And so these guys are at the same height, right? So if we compare point 2 and point 3, so even though they're in different fluids, here, so you can see that point 2 is in the blue fluid, but point 3 is in the purple one. So even though they're in different fluids, they're still at the same height. And so it doesn't matter if you're in the same fluid or different fluids, as long as you're the same height, you're always going to be at the same pressure, okay? And so since point 2 and point 3 at the same height, we can say that they have the same pressure, okay? Okay, so we know that P2 is equal to P3, okay? Right? And then finally, we can go from point 3 to point 4, right? And these guys are going to be separated by a height h2 in fluid 2. Okay? And so what we can use is we can use the same formula here to basically compute the pressure differences between point 3 and point 4. Okay? But before I do that, are there any questions on this slide before I continue?
I have a question.
Sure. What's up?
I'm getting confused by the subscripts with pressure difference in number 2. So we have it as P1 minus P2, but the equation has it as P2 minus P1. Is P1 in the front because it's the fluid on top?
Yeah. So the equation that we had before, you're right. It's P2 minus P1. But the reason we had that before was because, you know, in the kind of the example that we did, we had 0.2 on top and then 0.1 on the bottom. Well, in this case, just because of, you know, we're kind of working our way from the left and going to the right, I have 0.1 that's on top. And so since we have 0.1 on top, that's why I did P1 minus P2 here. So if you want to kind of remember in your mind, you can think of it as like top pressure minus bottom pressure is equal to minus gamma times H. Yeah.
Okay, got it. Thank you.
Mm-hmm. All right, any more questions on this before we finish up the derivation? Okay. So from point 3 to point 4, let's go to our formula. So in this case, you know, point 4 is on top, so we're going to list that pressure first, right? So we're going to have P4 minus P3, okay, and this is equal to minus gamma. And so since we're in the gauge fluid, so the gauge fluid is fluid 2, so we're going to have gamma 2 times H2. Okay, so we can simplify this a little bit more. And so since we know that 0.4 is going to be, that's at our free surface, then we know that P4 is going to be equal to 0, okay? And so we get P3 is equal to gamma 2 H2, okay? Right. Right, so that's all the different points. And so now what we can do is we can take all the equations here that we boxed and then get that, use them to find an expression for PA. Okay, because remember PA is kind of what we were looking for as we started this problem. Okay. Okay, so let's start backward. Let's start at the back and move forward. Okay. So we have P3 is equal to gamma 2 H2, but from step 3 right here, we know that P2 is equal to P3. So let's go ahead and replace P3 over here with P2, okay, because they're the same. As remember, they're at the same height, okay. And then just for convenience, what I'm going to do is I'm going to rewrite this equation right here, okay. So we have P2 minus PA is equal to, what was it, gamma 1 H1, okay. Right. Yeah. Yes, I can hear you, but it's staticky. Oh man, Zoom's having trouble. I could hear you. I'm getting like bits and pieces, but I can't hear the whole thing. It
Yeah,
seems
the
like
last connection. I think if you read the chat, everybody's writing to you.
yeah. Everyone's a connection job. Yeah, sorry about that, everybody. You know, if
I think you ended in the last thing we heard was use expressions for PA.
yes, okay. Right. So so basically what we're doing is we're kind of working our way around the YouTube manometer here and going from point to point and location to location. And so we have all these expressions here from all the different parts. So we have a step 1, step 2, step 3, step 4. And then basically what I'm doing here is I'm plugging everything back in so that we can solve for PA right here, okay? And so at the end of step 4, we basically have P3 is equal to gamma 2 H2. And so since we know that P3 is the same as P2, what I've done was I've replaced the 3 here with 2. Okay. And then what I'm going to do next is I'm going to take this P2 and then plug it into our equation from step 2 over here. Okay. So all I've done is I've rewritten this expression right here onto the next page, okay, just for convenience. And so let's take P2 and then let's plug that into this equation right here so that we can solve for PA. Okay, so we have gamma 2 H2, okay, minus PA is equal to gamma 1 H1, okay? And so we can now solve this expression for PA. We get PA is equal to gamma 2 H2 minus gamma 1 H1, okay? And so that's the pressure at point A in this YouTube manometer, you know, based on the specific weights of the fluids and the height difference between the different columns. Right. So I know there was a lot of connection issues with that example, but are there any questions on this? Okay. Yeah, sorry about all the technical issues, guys. It's hard for me to because you know I see the chat, but I'm not looking at it all the time because I'm writing on here. So definitely, if you're having issues, just and you can turn on your microphone. That usually catches my attention faster than the chat. Okay. Okay. So the question in the chat is: so we use all the relations we found to find an equation to find PA. That is correct. Yes. Yeah, so this example that we just did was kind of a nice example because, you know, before when we were using our hydrostatic equation, we just used it in kind of a simple situation. So here, what we had to do is we had to use kind of the same expression multiple times and kind of worked our way around a U2 manometer in order to find the pressure at our desired location. So it's just kind of a way to kind of, for you guys to see, you know, how do we actually use this, you know, in kind of a more complex situation. Okay, so the question in the chat is, how are P2 and P3 the same? So yeah, so it was answered in the chat. So it's because they're the same height, they're at the same pressure. Yeah, yeah. So that part might have gotten cut off due to the lag, but even if you're in different fluids, as long as you're in the same height, then you have the same pressure. Yeah. Mm-hmm. Yeah, so as long as you're in the same container, you know, it doesn't matter if you're changing between different fluids, you know, same container, same height, then you're going to have the same pressure. Yeah. Okay, so let's do one more example that kind of illustrates the same thing. Okay. So let's say that we have a container filled with oil. And it's a closed container. Okay. So let's say we have oil here and we have air that's on top. confined air, so it's not a free surface, right? And then attached to this, we have a U-tube manometer. Okay? Okay. And so let's say that we have, our two fluids are like this. Okay. So let me use some colors to better illustrate this. So let's use orange for the oil, and then we'll use purple for the gauge fluid. Okay. So this right here is our gauge fluid, which is going to be liquid mercury. Okay. And then let's put in some heights. So let's say that we have first this height from here to here will be H1. Okay. And then this height from here to here will be H2. Okay. And then this height from here to here will be H3. Okay. So I know it's from this drawing, it looks like H3 is equal to H1, H2, but this manometer is actually a bit different. So actually, just to make this a bit more clear, let me make this a little bit taller. Okay. And so this height up here is H3. So that's just to emphasize that H3 is different from H1, H2. Okay. Okay, and then so what we're interested in here is we want to see what the pressure is at the oil and air interface. Okay. Okay. And so let's put some numbers on this. And so let's express the specific weight of the oil in terms of its specific gravity. Okay. So remember, specific gravity is the ratio between the specific weight of this fluid compared to the specific weight of water. And so let's say that's the specific gravity of oil is 0.9. And so what that means is that the oil has a specific weight that's 90% of what the specific weight of water is. Okay. Okay. Next, we need the specific weight of the gauge fluid. So the specific weight of the mercury is going to be 13.6. Okay. And so that tells us that mercury has a specific weight, or it has a density that's 13.6 times higher than that of water. Okay. Okay. And then these are all the stats for all the heights. So we have H1 is equal to 90 centimeters, H2 is equal to 10 centimeters, and H3 is equal to 25 centimeters. Okay. So this is a little bit inaccurate. So actually, maybe H3 should be shorter than that, but it's okay. They're all different. That's all that I wanted to express. Okay. Okay. Are there any questions on this before we solve it? So we have about 7 minutes left. So I'm going to try to solve this kind of as quickly as I can.
Yeah, Professor, for the H3, does
Yep.
that reach to the separation in the oil and the mercury, or is it just a little bit below it?
So the bottom parts of H3 and H2, so these two guys are at the same height.
Okay, all right, thank you.
And then it reaches just up to the surface. So maybe the more realistically, I should have cut it off here, but that's okay.
Okay, thank you.
Yeah. Mm-hmm. SG stands for specific gravity. So I'll show you just on the next page how do we actually use that to compute specific weight. Yeah. Yeah, SG is something that's really special, but it's not that difficult to use. You just have to multiply basically by the specific weight of water. Mm-hmm. Okay. Okay, so let's do that first. So let's take the specific weight of let's compute the specific weight of oil and the mercury. Okay. And so what we know is we know the specific gravity of the oil, and this can be 0.9. And all this is the specific weight of oil divided by the specific weight of water. So in order to get the specific weight of oil, we take 0.9 and we multiply by the specific weight of water. Okay? And so the specific weight of water is 9,800 newtons per meter cubed. And so if we plug that in, what we get is specific weight of oil is 8,820 Newton per meter cubed. Okay. Right. And then the specific weight of mercury is 133,280 newtons per meter cubed. Okay. So mercury is really, really heavy, right? And that's why it makes such a great gauge fluid, because it's really heavy. So the nice thing about using a heavy gauge fluid is that you can get, you can measure, you know, the height differences will be small, so it doesn't take up that much space, but it can handle, you know, big differences in pressure. Okay. Okay. So any questions on that? And so what we're going to do next is we're going to basically do the same process that we did with the YouTube manometer. So we're going to kind of work our way around the YouTube until we get to the location that we want. Okay. Okay. So let's do the same thing. So let's work our way around the manometer. But just so you guys get a little bit of a different look, let's work backwards. So let's start from the free surface and then kind of work our way around to the location that we want. So let's go from free surface to bottom of H3. Okay. And so back in the problem, basically where I'm going to go is from up here. So we'll call this location 3, and we'll call this down here location 2, and we'll call this location, since location 2 and location 2 are the same, so let's call that location 2. And then we'll call this guy location 1. Okay, so we're basically going to go from 3 down to 2 right here. Okay, okay, so we go P3 minus P2. Okay, this is going to be equal to minus gamma Hg times H3. Okay. And so in this case, since we know that location 3 is at the free surface, we can set this equal to 0. Okay. And so what we get is P2 is equal to gamma Hg times H3. And we plug in the numbers, and this is 33320 Pascal. And so that's the location at the bottom of H3 in our diagram. Okay. Okay. And so the next thing that we want to do is we want to go from location 1, which is at the oil air interface, down to location 2. Okay. Okay. So let's do P1 minus P2. And so in this case, since we're traveling through the oil, we're going to do gamma oil, okay? And then we need to have the total height difference between them, okay? So we're basically going from this location right here, which is the same height as this one, okay? And then we're going to go all the way up here, okay? So this right here is location 1, and this is location 2, right? So since location 1 is up top, we're going to put that one first in our equation. And then the total height in between location 1 and location 2 is going to be the sum of H1 and H2. Okay. Right. And so this is what we want to solve for in the end right here. Okay. And so we have P1 minus P2 is equal to minus gamma oil, H1 plus H2, right? So we have everything here, and we have P2 because we have P2 from the previous step. Right? So we have P1 is equal to P2 minus gamma oil times H1 plus H2. Okay. Right. And if we plug in all the numbers here, we get 24,500 pascals. And that's going to be P1. Okay. All right. So I went, quite a bit faster this time, but it's the same process that we did with the YouTube manometer derivation. So, for these kinds of problems, you basically just have to work your way around the manometer. You can go either way. So you can either go from the free surface, around to your point of interest, or you can do it like we did in the derivation. You can go from your point of interest over to the free surface. As long as you're kind of consistent in how you apply the formulas, you should get the same result either way. Okay. All right. Are there any questions on this example here? Okay, so if there's no questions, then that's all we got time for this week. So thank you everyone for tuning in. I apologize again for the technical difficulties, but thankfully on my end it seems to have connected the whole time. So the lecture video will be kind of one consistent thing. Okay. So before you guys go, there's the minute paper for this week should be up on the Canvas site. So if you have time, definitely go fill that out because that information is really valuable to me. Okay. Just in how I design the class and everything. So, if you can, that's great. Okay. So there's a question. So is there no class on Monday? I think that there's class on Monday. Let me see.
We've been told that it's not.
I don't think there is.
Oh, there's no, okay. So yeah. Okay, so there's no class on Monday. So I guess I'll see you guys on next Wednesday then. So a week from today. Oh, it's Labor Day. Yeah, campus is closed. Right.
Yeah.
Okay, so thank you everyone for tuning in. Have a great weekend, and I'll see you guys next Wednesday then.
Thanks, Professor. Thank you, Professor.
Yeah.
Thank you guys. Have a good weekend.
You too.